Welcome back. Today we are going through lesson 6-7, which is all about the polynomial theorems. So the first polynomial theorem that we are going to talk about is called the factor theorem. So we're going to go through kind of an example here and see what the factor theorem tells us. So the factor theorem starts with factoring, which makes sense. So this one is a trinomial, so I can factor it into two binomials by finding the products of -8 that add up to -2, and that would be x minus 4 and x plus 2. So those are the factors of that polynomial. So if you remember from previous lessons, that means that the solutions are x equals 4, because 4 minus 4 is 0, and x equals -2, because -2 plus 2 gives us 0. So those solutions, remember, represent the x-intercepts on our graph. They also represent what we call zeros, again, because those are what make our factors equal 0, and then another name we use for them are roots. And we'll get more into roots in a little bit. So those factors give us our x-intercepts, our zeros, our roots. If we think back, if I substitute those values in for x, so if this equation up here is f of x, if I plug in 4, remember that's going to give me 4 minus 4, which is 0, and 0 times anything is 0. So if I substitute 4 back in, I get out a 0. That means that my ordered pair is 4, 0. The input of 4, output is 0. And then the same thing happens. If I input a -2, I will also get 0. So that means an ordered pair is -2, 0, and those are my x-intercepts. So what that develops for us is what's called the factor theorem. So when the solutions are substituted in for x, you will always get y equals 0. So in other words, what that means is that when you have a factor and you get its solution, you're going to get a 0 out. So if something is a factor, so if x minus r, and that could be any factor that we had x minus 4, we had x plus 2, x minus r is just an example. If x minus r is a factor, then the function with r substituted in has to equal 0. So if we substitute a number in and we get out a 0, we know that x minus that number is a factor. So that's one way to check to see if something's a factor without actually having to factor the polynomial. All right, the second theorem that we are going to talk about here is called the remainder theorem. So the remainder theorem, as you probably remember from previous knowledge, has to do with the remainder after dividing. So we're going to use synthetic division to divide this polynomial by x plus 3. So remember synthetic division, we're going to use the solution that goes with it and the coefficients. So 4, 6, -2, and 1. So when we do synthetic division, we drop the first one down, multiply those together, add those together, multiply by -3, add those together, multiply by -3, and add those together. Now let's look at it in a slightly different way. So let's find the solution for f of -3. So if I take that -3 and I plug it in up above for x, so in other words, if I substitute it in to our polynomial, when I do that math out, what ends up happening is that I also get -47. So what that means is that when I substitute in the solution for the factor that we're dividing by, it will give me the remainder. So it's kind of a shortcut or a way to find that remainder without having to do your division. So here's what the theorem says. It says if the polynomial is divided by x minus a, so that's what we did in our synthetic division, then the remainder is f of a. So we can find that remainder by substituting the a value in instead of dividing. All right, so we're going to practice a little bit here with these theorems. So here's what we're going to do. We're going to use the remainder theorem first, and that's going to tell us if something is a factor or not. So the first binomial that we're going to divide, so we are doing this first one here. We are going to divide that polynomial by the binomial x minus 1. And so remember, if we do f of 1, f of that a, if I plug in 1, and I do the math, I plug in 1 for x in that polynomial, I get a -4. So that means that -4 is the remainder. And since -4 is the remainder, that means it is not a factor. Because remember, if it's a factor, we get out 0. Okay, so let's look at the next one. This time I am going to plug in -3. And when I do that, I get 0 out. Since I get a remainder of 0, that means that yes, it is a factor. All right, and then lastly on this one, I am going to plug in a 5, substitute that in, 5 cubed minus 2 times 5 squared minus 12 times 5 plus 9. That comes out to be 24. So the remainder is 24, which means it is not a factor because it is not a remainder of 0. Okay, let's look at our second polynomial here. So now we are taking this one and we are plugging in our value. So on this one, my solution, remember, would be 1/3. So we'd add the 1, divide by 3. So when I plug in 1/3 here, and again, you can certainly use your calculator, I get out a 0. So because it's a 0 remainder, that means it is a factor. For this next one, my solution would be -1. So if I substitute -1 into that polynomial, I get 52, which is not 0. So this is not a factor. All right, and then last one for this polynomial, if I plug in -3, I substitute that in, I get out 270. So since it's not 0, it is not a polynomial. All right, and then our final polynomial over here. Number 3, we're going to substitute in here. These are getting quite long, so again, use a calculator to substitute in. And this one, when I substitute in 1, I get out a total of 77. Since that remainder is not 0, this is not a factor. X minus 1 is not a factor of that polynomial. All right, now let's plug in -5. If I substitute in -5 there, I get -157, which is not 0, so that is not a factor. And lastly, this final one is asking me to substitute in -6. When I substitute that in, I get a 0 out, so that is a factor. So the remainder and the factor theorem kind of go together there. They let you work simultaneously. Okay, let's talk about our final 2 theorems today. So these 2 theorems, the first one's called the rational root theorem. So we're going to use this polynomial as an example to kind of figure out what the rational root theorem is. So the rational root theorem, you take a polynomial and you find all the factors of the constant term. So here's my constant term. That is 6. And then you're going to find the factors of the leading coefficient as well, which is 2. So we're going to write out all the possible factors of 6. So we know that 1 goes into 6, and again, it could be positive or negative depending on what we're multiplying it by. So that's where the plus or minus is coming from. 2 is a factor of 6. 3 is a factor of 6. 4 is not. 5 is not. 6 is a factor of 6. So those are all my factors of 6. That's going to be our p-value, we call it. Then we're going to take all the factors of 2, which are just 1 and 2, of course. And what the rational root theorem allows us to do is then combine those and list out all the possibilities for p divided by q. So in other words, we're going to take all the values of p and divide it by the factors of q. So we're going to take 1, 2, 3, and 6 and divide it by 1, by 2, and do it for each one. So starting with the first one, we have 1 divided by 1, that's 1, and 1 divided by 2, that's a half. And then we start with 2. 2 divided by 1 is 2. 2 divided by 2 is 1. We've already written that one down, so I don't need to write it again. Then I go to the 3. 3 divided by 1 is 3. 3 divided by 2 is 3/2. And then I go 6. 6 divided by 1 is 6. 6 divided by 2 is 3. That one's already written there. So here's how the rational root theorem works. It's only works for polynomials with integer coefficients. So we couldn't use it if it had a fraction or a decimal or anything like that. We identify all the possible rational solutions. So that's where our factors came in. And we know that a root must be a factor of p and q in the form p divided by q. So remember, p is the factors of the constant term. So that's that number at the end when it's written in standard form, divided by the factors of the leading coefficient. So that gives us all of our possible rational roots. Our final theorem is called the complex conjugate theorem. So you have to recall some old knowledge here. Remember that the complex conjugate takes something of the form a plus bi, and the conjugate switches the sign. So in this case, the conjugate of 2 plus 3i is 2 minus 3i. All right. So we're going to use that as we kind of solve some polynomials here. So the first thing it asks us to do is it asks us to use a quadratic formula to solve. So remember, you have your a value, your b value, and your c value. And then we plug them into the quadratic formula, which is the opposite of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So if we simplify that, we get 6 plus or minus the square root of 36 minus, when I simplify 4 times 3 times 9, I get 108 all over 6. Simplify that square root a little bit more. 36 minus 108 is negative 72 over 6. And then if I simplify the square root of 72, 36 goes into 72. So that would turn into, let's see, 6. It's imaginary because of the negative, and I'd be left with the square root of 2 all over 6, which means it simplifies to 1 plus or minus I root 2. So these 6's reduced to 1, these 6's reduced to 1. All right. Now, let's solve using a different method. So we're going to solve with the square root method here. So remember the square root method, we take our equation of a quadratic, we set it equal to 0, and then we start isolating that x. So I would subtract 5 from both sides and get x minus 2 squared equals negative 5. I would square root both sides and get x minus 2 equals plus or minus I for the negative, square root of 5. And then add the 2 to both sides. And my solution would be x equals 2 plus or minus I root 5. All right, so noticing what we just talked about for our solutions here, for our solutions that we just got, anytime we solve and get a solution of a plus bi, we should notice that we always also get the negative of it, right? That square root of an imaginary, results in imaginary, always has plus or minus. So it is not possible to have one without the other. So the complex conjugate theorem says that if a plus bi is a root, then a minus bi must also be a root, and vice versa. If you find a minus bi, then a plus bi has to be a solution too. So these examples we did here are just ways to show you that no matter what, we're going to get the positive and the negative, because in order to get a complex answer, we're going to take a square root, which has plus or minus in the answer. So let's look at 2 examples of that here real quick. So the first one says identify the possible roots. So this is where your rational root theorem comes in of this polynomial. So remember, for the rational root theorem, we're going to take the factors of negative 12. So let's write those out. We would have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. 5 does not go into 12, but 6 does. 7 does not, 8 does not, 9, 10, 11, but 12. So those are all the possible roots, factors of 12. Now let's find those factors of the leading coefficient. So in this case, we have plus or minus 1 and plus or minus 3. And then we need to write out all the possible rational roots, which is where we take p, all the possible p factors, and divide by the q factors. So in this case, we're going to take 1 divided by 1 and 1 divided by 3. Then we're going to take 2 and divide it by each one. So that would be 2 and 2/3. We would have 3 divided by 1 and 3 divided by 3, which is 1. We've already written that one. Then we do 4, so plus or minus 4 and plus or minus 4/3. Then we take 6, so plus or minus 6. 6 divided by 3 is 2. That one's already written up there. And then the factors of 12. So 12 divided by 1 is 12. And 12 divided by 3 is 4, which is already up there. So those are all the possible rational roots of that polynomial. Question 2 says that if 2 plus 3i is a root, then what also must be a root? So remember, the complex conjugate theorem says 2 plus 3i is a root, then 2 minus 3i is also a root, no matter what. All right, those are your polynomial theorems. We'll see you next time.